Hello and welcome to Nighttime Science. Tonight, the focus settles softly on time and space, two quiet dimensions that surround every moment of your life, whether you are awake, dreaming, or slowly drifting into sleep. As you listen, the body can rest completely still while the mind is invited to wander, unhurried through ideas that stretch from the smallest heartbeat to the long ages of the universe. There is nothing to solve and nothing to remember. Only a slow unfolding of gentle scientific facts about how time moves, how space extends, and how your own awareness fits into this wide and silent setting. In physics, time and space are not just poetic words, but fundamental quantities used to describe where and when events take place. Space gives every object a position or a location, while time tells the order in which events happen and how long they last. When a scientist notes the position of a star, or the instant a planet passes a certain point in its orbit, they are quietly working with these two ideas, marking coordinates in space and moments in time. In modern cosmology and physics, these two concepts are woven together into what is called space-time, a single framework that treats space and time as deeply connected. This perspective became central in the early 20th century with Albert Einstein's theories of relativity, which showed that time does not tick identically for every observer, and that gravity is linked to the geometry of space-time itself. In this view, planets, stars, and galaxies do not simply sit in a static arena, but gently shape the structure of space-time around them, influencing how objects move and how clocks tick. Even though the underlying physics can become complex, the core idea can be held very softly. Space describes the where, time describes the when, and together they form the setting in which the universe unfolds. Your own life, with its days and nights, its memories and expectations, is a small, intricate pattern within this much larger story. While you rest, countless processes continue beyond your awareness. The Earth turns, the Moon orbits, and sunlight glides across the face of the planet, all measured in the quiet language of time and distance. Cosmology, the scientific study of the origin, structure, history, and future of the universe, rests on this combined understanding of space and time. Observational cosmologists use telescopes and instruments to measure how galaxies are arranged, how they move, and how light from distant objects has changed during its long journey to Earth. Physical cosmologists build models that describe how the universe has expanded, cooled, and formed structures over billions of years, using the mathematics of space-time and the known laws of physics. In these models, the universe is not static but dynamic, with space itself stretching over vast timescales and carrying galaxies with it. Light travels across these changing distances at a finite, constant speed, bringing information from the remote past to your eyes and instruments today. Because of this, looking outward across great distances is also a form of looking backward in time, seeing galaxies and gas clouds as they were when their light first began its trip toward us. Time also has a quietly personal dimension, one that lives not in equations but in experience. Psychological research explores how the mind perceives duration, how attention and emotion can make a minute feel stretched or compressed, and how memory shapes the sense of a past and a future. Even though your inner sense of time is subjective, it is still grounded in physical processes. The firing of neurons, the release of neurotransmitters, and the rhythmic patterns of brain activity that rise and fall as you move from wakefulness into sleep. The body carries its own clocks, independent of watches and calendars that track the cycle of day and night. These internal timekeepers form the circadian rhythm, a roughly daily pattern that regulates sleep, alertness, body temperature, hormone levels, and many other functions. In humans, this rhythm is not exactly 24 hours long. It tends to run a little longer, around 24 hours and 10 to 20 minutes, and is gently adjusted each day by light from the environment. As evening deepens, the brain responds to fading light by changing the release of key hormones, including melatonin, which helps signal that it is time to wind down. Body temperature drifts slowly downward, reaction times lengthen, and the mind becomes more open to drowsiness and sleep. All of this unfolds according to patterns that have been shaped by millions of years of evolution on a rotating planet, where the alternation of day and night is one of the most regular features of the environment. On a planetary scale, time is measured by motion. A day is defined by the rotation of the Earth on its axis, the slow and steady turning that brings the sun into view, carries it across the sky, and then hides it again below the horizon. A year is defined by the Earth's orbit around the sun, the large, nearly elliptical path that takes about 365 1/4 days to complete, leading to the seasons as the planet's tilted axis presents different hemispheres toward the sun. Over even longer scales, time becomes the domain of geology and astronomy. Rocks record the slow uplift and erosion of mountains, the advance and retreat of ancient seas, and the gradual drift of continents across the globe. In the skies, stars form from clouds of gas, shine for millions to billions of years, and eventually change into denser remnants such as white dwarfs, neutron stars, or black holes, all according to the steady rules of nuclear fusion and gravity. The universe itself has an estimated age of about 13.8 billion years. Deduced by combining observations of the cosmic expansion, the light from the oldest stars, and the faint uniform glow known as the cosmic microwave background. This age is not guessed but calculated from multiple lines of evidence that converge on a similar result, lending strong support to the current cosmological model. Within that long history, human lifetimes, spanning decades, occupy only a very small segment, yet they are rich in experience and awareness. Even though this cosmic history is vast, there is no need to feel overwhelmed. Instead, it can be approached as a gentle background, a broad, steady canvas of slow changes against which the more immediate rhythm of your own days and nights quietly unfolds. While you lie in the dark and listen, the mind can drift between these scales, from the slow ticking of biological clocks and the sense of a single evening, out to the long arcs of planetary orbits and the expansion of the universe. Time is also linked to motion in a more precise way through the theory of relativity. When objects move very quickly, close to the speed of light, or when they are deep within strong gravitational fields, the rate at which time passes for them can differ from the rate measured by observers elsewhere. This effect, known as time dilation, has been confirmed in many experiments with fast-moving particles, atomic clocks on airplanes, and clocks placed at different heights in Earth's gravitational field. These differences are usually tiny in everyday life, too small to notice without sensitive equipment. But they reveal that time is not as rigid as it appears. A clock held slightly higher above the ground, where gravity is marginally weaker, will tick a little faster than an identical clock closer to the center of the Earth. Atomic clocks are accurate enough that this difference can be measured over height changes of just a few tens of centimeters, demonstrating that gravity gently influences the flow of time everywhere, not only near massive stars or black holes. All of these ideas, from biological rhythms to relativistic time dilation, can coexist in a calm mental space. The aim here is not to rush through facts, but to rest alongside them, letting each one settle in its own unhurried way. As you breathe, you can picture your own body as a small but complete system keeping track of day and night, while orbiting within a solar system which drifts within a galaxy, all moving through a universe that has been evolving for billions of years. In the sections to come, the focus will move more slowly through each of these layers. First, there will be a deeper exploration of the internal clocks that govern sleep and wakefulness. Then the attention will shift outward, to the way the brain perceives time, to the motions of the Earth, and then gradually to the cosmic scales of stars, galaxies, and the expanding universe. Always returning gently to the simple fact that, in this moment, you are resting, while time and space continue their quiet, measured behavior. Inside the body, many systems quietly track the passage of time, even when you do not look at a clock or a phone. These internal timekeepers are known as biological clocks, and together they help the body anticipate regular changes in the environment, such as the daily cycle of light and darkness. The most prominent of these rhythms is the circadian rhythm, a roughly 24-hour cycle that influences sleep and wakefulness, hormone levels, body temperature, digestion, and many other processes. At the center of this timing system, deep within the brain, lies a small region called the suprachiasmatic nucleus, often shortened to the SCN. This structure sits in the hypothalamus, just above the crossing of the optic nerves, and contains thousands of neurons that act together as a kind of master clock. These cells follow a near-daily rhythm of activity, generated by gene expression cycles and feedback loops inside the cells themselves, creating an internal pattern even when external light cues are absent. On its own, the human circadian cycle tends to drift slightly longer than 24 hours, averaging around 24 hours and some additional minutes. If a person is kept in constant dim light, without clear signals for day and night, the timing of their sleep and wakefulness gradually shifts later each day, reflecting this inherent period. To prevent this drift from continuing indefinitely, the SCN uses light from the eyes as a signal, gently adjusting the internal rhythm so that it stays synchronized with the 24-hour rotation of the Earth. Light information reaches the SCN through a special pathway. A subset of cells in the retina, distinct from those used mainly for forming visual images, are sensitive to light, especially in the blue portion of the spectrum. These cells send signals along a dedicated route to the SCN, allowing even diffuse daylight to inform the brain about the time of day, even when a person is not directly staring at the sun. In the morning, when bright light reaches the eyes, the SCN responds by shifting its internal phase, gradually promoting wakefulness and increasing alerting signals to the rest of the brain and body. Levels of certain hormones, such as cortisol, naturally rise around the time of waking, helping to prepare the body for activity. Body temperature also follows a daily cycle, tending to be lower during the night and early morning, and gradually rising through the day, supporting metabolic processes and physical readiness. In the evening, as light fades, the pattern reverses. The SCN communicates with other parts of the brain, including the pineal gland, which responds by producing melatonin, often called the sleep hormone. Melatonin levels typically begin to rise a couple of hours before a person's usual bedtime, providing a biochemical signal that it is time to wind down, dim lights, and move toward rest. Melatonin does not force sleep, but it nudges the body toward a state in which sleep comes more easily, supporting the alignment of internal rhythms with the external cycle of day and night. Exposure to bright light in the evening, especially light rich in short wavelengths, can delay this signal, pushing the internal clock later and making it harder to fall asleep at an earlier time. This is one reason that reducing intense light and screen exposure in the hours before bed can help the body maintain a consistent, sleep-friendly rhythm. Alongside melatonin, many other processes show circadian patterns. Digestive activity has daily fluctuations, with certain enzymes and hormones peaking at times that match typical eating patterns. Blood pressure tends to dip during the night and rise again toward morning, contributing to a phenomenon known as the morning surge, when cardiovascular activity increases as the body transitions from sleep toward wakefulness. Even within the brain, electrical activity and chemical signaling vary with time of day, influencing attention, reaction times, and emotional tone. During the biological night, when melatonin is elevated and core body temperature is lower, the brain is more inclined to move into and maintain sleep, especially when the environment is dark, quiet, and cool. During the biological day, the same brain circuits support sustained wakefulness, interaction, and learning. These rhythms continue even when regular schedules are disrupted. But mismatches between internal time and external demands can make a person feel out of balance. When traveling rapidly across time zones, for example, the external day-night cycle changes abruptly, while the internal circadian clock lags behind, still operating on the previous schedule. This difference produces jet lag, experienced as fatigue, sleepiness at unusual times, digestive discomfort, and difficulty concentrating. Gradually, exposure to the new pattern of light and darkness allows the internal clock to adjust, but this realignment can take several days, depending on how many time zones are crossed and in which direction. Eastward travel, which requires the clock to advance, can be more challenging than westward travel, which involves a delay that aligns somewhat better with the natural tendency of the circadian period to run slightly longer than 24 hours. Simple strategies such as seeking morning light in the new time zone or reducing light exposure late at night can help guide this adaptation. Not all biological rhythms follow a daily pattern. The body also exhibits ultradian rhythms, which are shorter cycles, such as the roughly 90-minute periods of sleep stages, and infradian rhythms, which last longer than a day, such as some hormonal cycles. Still, the circadian rhythm is a dominant organizing influence, providing a broad, repeating framework within which many shorter or longer patterns are embedded. Within individual cells, the circadian clock is closely tied to genes and proteins that regulate one another in self-sustaining cycles. Certain clock genes are transcribed and translated into proteins that, over time, accumulate and then feed back to inhibit their own production, creating oscillations in their levels. These molecular rhythms affect downstream genes and cellular processes, leading to time-of-day differences in metabolism, growth, and responsiveness to stimuli. Because nearly every tissue has some clock-like behavior, and the SCN acts as a master coordinator, the entire body can function like a gently synchronized network of oscillators. Each organ and system follows its own pattern, but these patterns are kept in loose alignment so that, for example, digestion is most active when eating is likely, and repair processes are emphasized during the night when the body is more often at rest. When these internal rhythms become misaligned, such as through irregular sleep schedules or shift work, health and well-being can be affected over time. Sleep itself follows both homeostatic and circadian influences. The homeostatic drive to sleep builds the longer you are awake, as certain chemical signals accumulate in the brain, creating pressure for sleep. At the same time, the circadian system modulates when that sleep pressure is most likely to lead to actual sleep. opening a kind of window when the internal clock, hormone levels, and body temperature all support a sustained rest. When these two systems are in harmony, sleep tends to come easily at the same general time each night and feels more refreshing. When they are in conflict, such as when staying up far past the usual bedtime or waking much earlier than the body expects, sleep may be lighter, shorter, or more fragmented. Over many nights, consistent schedules help these systems remain aligned, reinforcing stable patterns that make it easier to fall asleep and wake up at desired times. From a calm perspective, the circadian system can be thought of as a gentle, internal guide, continuously measuring the passage of the day and helping the body decide when to be active and when to rest. The ticking of this inner clock does not need conscious attention and continues even when you are deeply asleep. It keeps track of time using biochemical changes and neural activity, quietly coordinating countless processes so that the body maintains balance as the world cycles between light and darkness. This inner timekeeping is closely tied to the external cycles of the Earth. The length of the circadian period is tuned to the length of a day, which is defined by one rotation of the Earth on its axis. Over long evolutionary periods, organisms have adapted to the predictable alternation of daylight and night, building physical and behavioral rhythms that match the planetary environment. As a result, lying in the dark at night does not simply mean the absence of light. It also means that a complex, evolved system inside the body has shifted into its night mode, altering hormone levels, immune function, and brain activity in ways that support rest, repair, and memory consolidation. The sense of drowsiness is one expression of this state, a subjective feeling that emerges from many aligned signals pointing gently towards sleep. Thinking about these processes can itself be soothing because they show that the body knows how to rest almost automatically when it is given the right conditions. Darkness, quiet, and regular timing are not merely preferences, they are cues that the circadian system has learned to interpret as signs that it is safe and appropriate to enter the deeper phases of sleep. In this way, even without effort, the body participates in the regular rhythm of the planet's rotation, aligning its internal night with the external night outside. As the internal clocks guide the body through the night, the experience of time may change. Dreams can make minutes feel long, or entire nights can seem to pass in what feels like an instant, especially when sleep is continuous and undisturbed. This difference between clock time and felt time reflects the interaction of the circadian system with the brain's mechanisms for perception and memory, topics that will be explored more deeply in the next section. For now, it can be enough to know that, as you lie here, a web of quiet timing processes is already at work, helping to guide you toward rest, regardless of immediate thoughts or concerns. The SCN is tracking the recent pattern of light and darkness. Melatonin levels are either rising or preparing to rise, and body temperature is following its own nightly curve. These signals taken together create a gentle push towards sleep, supporting the mind's natural tendency to drift and soften as the night goes on. The brain's sense of time is not a single mechanism, but an emergent experience arising from many overlapping processes that track change, expectation, and memory. Seconds and minutes on a watch are consistent and uniform, but the felt length of those same intervals can vary widely depending on mood, attention, and context. In this way, there are two kinds of time always present: the physical time that can be measured by precise instruments, and the psychological time that is constructed by the mind. Research in psychology has shown that emotional states strongly influence subjective time. When a person is anxious, frightened, or under stress, time often seems to slow down, stretching moments into what feels like longer spans. One interpretation is that heightened arousal increases the amount of information processed and stored about each moment. So looking back, the interval feels denser and therefore longer. Conversely, during pleasant, absorbing activities, time can feel as though it speeds up. When attention is deeply engaged, the mind spends less effort checking the passing of moments and fewer temporal markers are laid down in memory. Afterward, the interval may feel surprisingly brief, even if the clock shows that many minutes or hours have gone by. Calm, quiet states like those that accompany drowsiness and the transition towards sleep bring their own softer style of time perception. Attention becomes less sharply focused on tasks and more diffuse, spreading gently across sensations, thoughts, and memories. In this mode, time can feel unhurried and expansive, not necessarily fast or slow, but simply less structured as the mind lets go of frequent checks against external clocks. Experiments that ask people to estimate intervals of time, such as judging how long a light stays on or how long a tone lasts, reveal that these estimates are affected by both internal and external conditions. When people are more alert and stimulated, they tend to overestimate the length of short intervals, perceiving them as longer than they are. When they are more relaxed, sedated, or drowsy, they are more likely to underestimate the same intervals, experiencing them as shorter. There is evidence that certain brain regions contribute more directly to the processing of time. Structures such as the basal ganglia, the cerebellum, and parts of the frontal cortex have been implicated in temporal judgment, motor timing, and the coordination of actions over intervals ranging from fractions of a second to several seconds. These regions interact with neurotransmitter systems, including dopamine pathways that modulate both movement and perception of duration. When these systems are altered either by neurological conditions or pharmacological agents, subjective time can shift. Some disorders that affect dopamine signaling, for example, are associated with changes in how patients perceive and reproduce time intervals, suggesting that the internal calibration of temporal processing has been adjusted. Certain drugs that influence arousal or attention similarly modify the way people judge durations, supporting the link between brain chemistry, state of mind, and time perception. Memory also plays a significant role in how long past events feel. When recalling a rich, detailed period of life, filled with new experiences and vivid moments, that span often seems longer in retrospect than an equally long period characterized by routine and repetition. This is sometimes called the holiday paradox, in which a vacation full of varied activities seems to pass quickly while it is happening, yet later feels extended because so many distinct memories were formed. In contrast, stretches of time that involve similar repetitive experiences can seem to drag in the moment, but later, when looked back upon, appear brief and compressed. The brain has stored fewer distinct markers for those days, so the retrospective sense of their length shrinks. This difference between prospective and retrospective time illustrates how the feeling of duration depends not only on what is happening now, but also on how events will be encoded and retrieved later. As the brain moves towards sleep, its handling of time shifts again. In the lighter stages of non-rapid eye movement sleep, awareness of time begins to loosen, and there may still be some sense of the night's unfolding, though it becomes less precise. In deeper stages of sleep and during rapid eye movement sleep, which is strongly associated with dreaming, the usual anchors of clock time fall away, and dream narratives can seem to stretch or compress in ways that do not match the actual minutes that pass. Studies that wake sleepers during dreams and compare their reports with real elapsed time suggest that, on average, dream time is roughly comparable to waking time, but the subjective quality can differ greatly. A dream may feel long because it contains many events or emotional turns, even if only a short episode has occurred in real time. On other occasions, long stretches of real time may be occupied by dream content that the sleeper only dimly remembers or forgets entirely upon waking, making the hours seem to vanish. The sense of a continuous self moving through time is supported by memory and by the brain's ability to link past, present, and anticipated future. This continuity is constructed from moment to moment as the brain integrates incoming information with stored experiences and ongoing predictions. During sleep, many of the brain's regions remain active, reshaping and consolidating memories, pruning some connections and strengthening others, which in turn influences how time and events are experienced the next day. Although the subjective flow of time can be fluid and variable, physical time keeps a steady pace, and the brain's clocks, from the molecular level to large-scale networks, tick along within that framework. The circadian system sets a broad, daily rhythm, while shorter-term timing mechanisms track seconds and minutes for tasks and actions. Perception weaves these signals together, filtered by emotion and attention, to create the felt sense of time that rises and falls across the day and into the night. In calm settings, especially in the quiet before sleep, attention to time can soften. Without deadlines or urgent tasks, there is less reason for the mind to check the clock repeatedly, and the brain's resources can relax away from constant temporal monitoring. Instead, awareness can rest more on gentle sensations, the rhythm of breathing and the gradual slowing of thoughts, making time feel less segmented and more continuous. This softness in time perception can support rest. When the mind is not repeatedly jumping forward to future tasks or backward to past events, the present moment can expand, feeling spacious and unhurried. In this expanded present, drowsiness can grow without resistance, guided by the internal night signals that come from the circadian clock and from the homeostatic drive for sleep. It can be comforting to understand that even when the sense of time feels unusual, such as late at night or during periods of strong emotion, this is a natural outcome of how the brain works. Subjective time is not expected to match perfectly with physical time in every situation. It is shaped to prioritize survival, learning, and emotional significance. Knowing this, it becomes easier to let go of precise temporal control as sleep approaches, trusting that the body's more fundamental clocks continue their steady work. As you lie still, the brain is quietly measuring and organizing time in the background, but you do not need to follow those measurements. The minutes of this listening session will pass at their own rate, felt perhaps as shorter or longer depending on your level of wakefulness, your interest, and your degree of relaxation. Regardless of that felt duration, the core processes of drowsiness, melatonin release, and body temperature change continue to move you along the nightly path toward deeper sleep. In the next section, attention will shift outward from psychological time to the planetary motions that define days and years. These larger cycles, grounded in the rotation and orbit of the Earth, provide the stable external framework within which both biological and psychological time unfold. For now, it is enough to notice that the inner and outer measures of time, from personal feelings to planetary motion, are all quietly aligned in their own ways, gently supporting the approach of rest. Every night, as you lie still and the room grows darker, the planet beneath you is turning with a steady, unhurried motion. This rotation is what creates the cycle of day and night, a basic rhythm that has guided life on Earth for billions of years. One full turn of the Earth on its axis defines a day, giving structure to your sleep, your wakefulness, and the timing of almost every routine you follow. The Earth spins around an imaginary line that runs from the North Pole to the South Pole, known as its axis of rotation. This spin is counterclockwise when viewed from above the North Pole, which means that, from your usual perspective on the surface, the sun appears to rise in the east and set in the west. The sense of the sun crossing the sky is actually the result of your vantage point on a rotating sphere turning smoothly beneath the light of a star. A complete rotation of the Earth relative to the sun, which determines the length of an average solar day, is very close to 24 hours. There are slightly different ways to define a day, such as the sidereal day, measured relative to distant stars, which is about 23 hours, 56 minutes, and 4 seconds. The solar day is longer than the sidereal day because while the Earth rotates on its axis, it also moves along its orbit around the sun and must turn a little extra each day for the sun to reach the same position in the sky. This rotation is extremely smooth when felt on human scales. You do not feel it directly because everything around you, the air, the oceans, the buildings and trees, is moving with the Earth as part of the same rotating system. The speed of this motion depends on latitude. At the equator, where the circumference of the Earth is largest, the surface moves at roughly 1,670 kilometers per hour, or about 40 miles per hour, relative to the planet's center. Closer to the poles, the circular path is smaller, so the linear speed is lower, like a point closer to the center of a spinning record. Over very long time scales, the rotation of the Earth is not perfectly constant. Tidal interactions between the Earth and the Moon gradually transfer angular momentum from the Earth's rotation to the Moon's orbit. This process very slowly slows the Earth's spin and causes the Moon to drift farther away. As a result, the length of a day increases by tiny fractions of a second over millions of years. Fossil evidence from ancient corals and other organisms that built daily growth layers suggests that hundreds of millions of years ago, days were shorter and there were more days in a year than now. On shorter timescales, the length of a day can also fluctuate slightly due to the redistribution of mass within the Earth system. Movements in the atmosphere, ocean currents, melting and accumulation of ice, and even large earthquakes can alter how mass is arranged, which in turn makes tiny changes to the rotation rate. These variations are small, measured in milliseconds, but they can be detected using precise instruments and satellite observations. Because the Earth's rotation is not perfectly steady, time-keeping systems that rely on the rotation of the planet must occasionally be adjusted. International time standards use extremely stable atomic clocks, which measure time based on the natural frequency of transitions in atoms such as cesium. These clocks define the length of the second with extraordinary precision. However, because Earth's rotation drifts relative to this atomic time, a correction known as a leap second is occasionally added to keep coordinated universal time aligned with the actual position of the Earth relative to the Sun. Beyond rotation, the Earth is also moving along a large orbit around the Sun, which defines the year. The average time it takes for the Earth to complete one full orbit is about 365.25 days. Because this is not an exact whole number of days, calendars must incorporate adjustments to stay aligned with the seasons. One of the most familiar adjustments is the leap year. In the commonly used Gregorian calendar, a leap day is added every 4 years to account for the extra quarter of a day per year, with some exceptions for centuries that are not divisible by 400. This careful pattern keeps the calendar date of events such as the solstices and equinoxes from drifting too far over centuries. The Earth's axis is also tilted relative to the plane of its orbit by about 23.4 degrees. This tilt is what creates the seasons. As the planet moves around the sun, sometimes the northern hemisphere is tilted toward the sun, receiving more direct sunlight and longer days, and sometimes it is tilted away, receiving more indirect light and shorter days. The southern hemisphere experiences opposite seasons at the same time. This interplay of tilt and orbit means that the length of the day, the height of the sun in the sky, and the path of sunlight across your location change gradually throughout the year. During summer at a given latitude, days are longer and nights are shorter. The sun rises earlier, sets later, and at midday climbs higher in the sky. In winter, the opposite occurs. Days are shorter, nights are longer, and the sun stays lower, arcing closer to the horizon. At high latitudes near the poles, these effects are even more dramatic. Regions above the Arctic Circle and below the Antarctic Circle can experience periods of continuous daylight in summer known as the midnight sun, and continuous darkness in winter called polar night. These changing patterns of light and darkness strongly influence biological rhythms. The circadian system, which naturally tracks a roughly daily cycle, uses the varying length of daylight as a seasonal signal. In many animals and plants, this photoperiod information shapes seasonal behaviors such as reproduction, migration, and dormancy. In humans, even though modern lighting allows activities to continue at almost any hour, the seasonal variation in daylight can still affect mood, sleep patterns, and overall energy levels. The Earth's orbit is not a perfect circle, but a slightly stretched ellipse. This means that the distance between the Earth and the Sun changes over the course of a year. However, this change in distance is not the main cause of the seasons. The axial tilt plays the dominant role. The difference in distance slightly modifies the intensity of sunlight, but the greater factor is the angle at which sunlight strikes the surface and the length of time the sun remains above the horizon each day. Thinking about these motions in a calm nighttime setting can bring a sense of gentle order. While you rest, the Earth continues its rotation, carrying your location smoothly from night toward dawn. At the same time, the planet is quietly advancing along its orbit, bringing about gradual shifts in sunrise and sunset times, in the position of constellations at certain hours, and in the temperatures and weather associated with each season. These movements have been ongoing for long before recorded history, and will continue long after any individual lifetime. The regularity of these cycles provided some of the earliest natural clocks. Long before mechanical or electronic timekeepers, people could track days and seasons by watching the path of the sun and the changing constellations. The daily arc of the sun measured daytime, while repeated patterns in the sky and in the growth of plants signaled the passage of months and years. Modern scientific understanding has refined these observations, explaining them in terms of rotation, orbit, and tilt, but the basic experience remains the same. The sky changes in rhythms that can be anticipated. Because the Earth is part of a larger system, its motions are also influenced by other bodies, especially the Moon and the Sun. The gravitational pull of these objects raises tides in the oceans and even slight tides in the solid Earth itself. The pattern of high and low tides, which follows a roughly 12.4-hour cycle at many coasts, is linked to the rotation of the Earth beneath the bulges of water aligned with the Moon and to a lesser extent with the Sun. This daily and monthly dance of water levels adds another layer of rhythmic motion to the planet. Over extremely long periods, the orientation of the Earth's axis in space also changes slowly. This phenomenon, known as axial precession, causes the direction in which the axis points to trace a slow circle over about 26,000 years. Because of this, the identity of the pole star changes over millennia, and the timing of the seasons relative to the Earth's position in its orbit shifts gradually. Additional oscillations in tilt and orbital shape occur on tens of thousands to hundreds of thousands of years, contributing to cycles of ice ages and interglacial periods. Although these longer cycles do not affect nightly sleep directly, they demonstrate that the time structures you experience from one night to the next, from one season to the next, are nested within even grander patterns of motion. Your evening today is one rotation step in a very long sequence of rotations and orbits, each one governed by the same basic physical principles. This continuity can be quietly reassuring. The turning of the Earth is dependable, and the progression of night to day is one of the most stable features of life on this planet. As you lie still and let these facts drift through the mind, there is no need to visualize every detail. It is enough to know that around you motion continues in a slow, orderly way. The room may feel perfectly at rest, but beneath and around you, the Earth is rotating about its axis, orbiting the Sun and participating in a layered system of cycles. Those cycles define the length of your day, the rhythm of your seasons, and the backdrop against which biological and psychological time unfold. In the next section, attention will move from the scale of days and years to the wide range of time intervals that exist, from fractions of a second to billions of years. The flow will gently expand from the human sense of a day and a year into the deep time scales of geology and cosmology, always returning to the calming idea that, whatever the scale, time moves with a steady, impartial pace while you are free in this moment simply to rest. Time can be imagined as a smooth line stretching from the smallest moments you can notice all the way out to the age of the universe. At one end of this line lie fractions of a second, the duration of a heartbeat, the blink of an eye, the oscillation of an atom used in an atomic clock. At the other end lie billions of years, the time it takes for galaxies to grow and change, for stars to be born, live and fade, and for the universe itself to evolve from a hot, dense early state to the vast, gently expanding cosmos you inhabit now. In everyday life, many familiar actions take place on time scales of seconds. A single deep breath in and out may last a few seconds. A spoken sentence like the ones in this script unfolds over a similar interval. Seconds are long enough for you to become aware that something is happening, but short enough that they can pass almost unnoticed when your mind is relaxed or preoccupied. They are the units most often shown on clocks and timers, marking the steady passage of time in an audible tick or a digital change of numbers. A little higher on the scale are minutes. A minute is 60 seconds, long enough to feel distinct as a small block of time. Many simple tasks fit into the span of a few minutes. Waiting for water to boil, brushing teeth, or settling into bed and adjusting the pillow until the body feels comfortable. In calm settings, a minute can feel spacious, especially when you are focused on a simple, repetitive sensation like breathing. In more active moments, minutes can seem to vanish quickly, especially when attention is divided among many small tasks. On a larger scale are hours. An hour is 60 minutes, a familiar unit used for planning parts of the day. Hours of work, hours of rest, hours set aside for meals, reading, or sleep. A standard night's sleep is often measured in hours, typically somewhere around 7 to 9 for many adults. Over the course of a night, the brain cycles through different sleep stages in patterns of roughly 90 minutes each. So a full night includes several of these cycles. The mind does not usually register the individual minutes during deep sleep. Instead, the hours blend into a continuous stretch that begins at bedtime and ends with waking. Days, which were explored in the previous section, bundle hours into a natural cycle tied to the rotation of the Earth. One day includes time for waking, activity, and rest, as well as a portion spent in darkness when sleep is most likely. Weeks, months, and years build upon this unit, stacking days into larger patterns that mark social, agricultural, and personal rhythms. These units are partly natural, based on cycles like the moon's phases and the Earth's orbit, and partly conventional, defined by human choice and culture. Beyond years lie decades, a span of time long enough to encompass significant changes in a human life. Over 10 or 20 years, a person may move through different phases of education, work, relationships, and personal growth. Hair may gray gradually, skin may show more lines, and perspectives may shift, even though the change from one day to the next is subtle. On this scale, the body's slow biological aging becomes more apparent, and memories begin to cover a broader portion of a lifetime. A century, or 100 years, is longer than any single human life in most cases, though some individuals do reach and slightly exceed this span. On this scale, the world can alter in ways that no one person experiences fully from beginning to end. Technologies are developed and replaced, cities grow and change shape, and knowledge accumulates in scientific, artistic, and cultural records. For the Earth and the universe, however, even a century is still a very short interval. Moving upward 1,000 years, one millennium brings us into historical timescales. Over 1,000 years, civilizations can rise, flourish, and decline. Languages evolve significantly, and the physical landscape of human structures transforms. Natural systems like forests and river courses may change noticeably, but usually still retain some continuity. Geological and astronomical processes are underway, but most of them act so slowly that a millennium represents only a tiny step in their progression. Geological time often deals in units of tens of thousands to millions of years. Over tens of thousands of years, major climate patterns can shift, ice sheets can advance or retreat, and sea levels can rise or fall. Over millions of years, mountains can be uplifted or worn down by erosion. Continents can drift measurable distances due to plate tectonics, and species can evolve or go extinct. Fossils embedded in rock layers provide evidence of these changes, recording stacked snapshots of different eras, each representing a range of ages that dwarf human history. On still larger scales, tens or hundreds of millions of years describe substantial chapters in the history of life on Earth. Entire groups of organisms appear, diversify, and sometimes disappear. Dinosaurs, for example, lived for well over 100 million years before their non-avian lineages were largely extinguished, while other lineages continued and eventually gave rise to birds. During these vast intervals, continents rearranged, climates fluctuated, and the oceans and atmosphere changed in composition. Yet from the perspective of a single evening, these changes are far beyond direct perception. They form part of the background story of the planet rather than its immediate experience. When time reaches into the billions of years, it enters the realm of planetary and cosmic evolution. The Earth itself is about 4.5 billion years old, having formed from the dust and gas surrounding the young sun. In its early history, the planet was molten and heavily bombarded by asteroids, gradually cooling and developing a solid crust, oceans, and an atmosphere. Life is thought to have arisen relatively early in Earth's history, perhaps over 3.5 billion years ago, but for much of that time it consisted of single-celled organisms and simple communities, long before complex plants and animals appeared. The Sun, like other stars, has its own life cycle measured in billions of years. It is a main sequence star that steadily fuses hydrogen into helium in its core, releasing energy that radiates outward as light and heat. The Sun is currently in a stable phase of its life and has been shining in a broadly similar way for billions of years. It is expected to continue this relatively steady output for several billion years more, gradually brightening over time before eventually exhausting the hydrogen in its core and evolving into a red giant star, then shedding its outer layers and leaving behind a dense white dwarf remnant. Beyond the scale of a single star, the universe as a whole has an estimated age of about 13.8 billion years. This estimate comes from multiple converging lines of evidence: measurements of the expansion rate of space, observations of the oldest star clusters, and the characteristics of the cosmic microwave background radiation, the faint afterglow of the early universe. In the standard cosmological picture, the universe began in a hot, dense state and has been expanding and cooling ever since. Over time, matter condensed under gravity to form the first stars and galaxies, which then merged and evolved into the rich structures observed today. On these cosmic timescales, even the age of the Earth represents only a portion of the universe's history. When the Earth and Sun formed, the universe was already about 2/3 of its present age. Earlier generations of stars had lived and died, forging heavy elements in their cores and in supernova explosions which enriched the gas clouds that later collapsed to form new stars and planetary systems. The atoms in your body, such as carbon, oxygen, and iron, were created in such stars, linking your physical existence to processes that unfolded over billions of years before the solar system formed. The range of time from fractions of a second to billions of years is immense, and yet all of these scales are part of one continuous dimension. The second, defined in modern terms by the vibrations of cesium atoms in atomic clocks, provides a precise foundation. From there, units are built upward: minutes, hours, days, years, centuries, and beyond, each representing a simple multiplication of smaller units. This standardized system allows scientists to express accurately both the rapid flicker of a subatomic event and the slow unfolding of a galaxy's evolution. For sleep and relaxation, most of these enormous timescales do not need to be held in detailed awareness. Instead, they can be allowed to drift in the background as gentle reminders that your current experience occupies a very small but real place within a much longer story. The few hours of a night's rest are nested within a day, which is nested within a year, which is nested within the age of your life, which itself is nested within the multi-billion-year history of the planet and the universe. Thinking this way can be oddly calming. Immediate concerns and tasks typically live on relatively short time scales. Minutes, hours, days. When attention steps back to consider longer spans, those short-term pressures can feel less absolute. They are still important, but they become part of a larger context, like brief ripples on a very broad, slow-moving river. In that wider view, the act of lying down and allowing the body to rest becomes one small but meaningful pattern in the flow of time, aligned with cycles that have guided living organisms for countless generations. As you continue to listen, the script will turn next to the distances of space and the speed of light, connecting the long time scales just described with the immense sizes of the cosmos. Distances and times are closely linked in astronomy because light takes time to travel. So seeing far in space means looking far back in time. Holding that idea gently in mind, the attention can now drift outward, preparing to explore how light carries information across the universe at a finite but very high speed. Time and space are closely linked in the universe, and one of the deepest connections between them is carried by light. Light does not move infinitely fast. It travels at a finite speed, though that speed is very high. In a vacuum, light moves at about 300,000 kilometers per second, which is roughly 186,000 miles per second. Because of this, whenever you look at something, you are seeing it as it was a short time ago, the time it took light to leave the object and reach your eyes. On everyday scales, this delay is so small that it feels instantaneous. Light takes only a tiny fraction of a second to cross a room or reflect off an object on a nearby table. Even light from the moon, which is about 384,000 kilometers away, takes only about 1.3 seconds to reach Earth. That means when you look at the moon, you see it as it was just over a second ago. The difference between that and the current moment is so short that, for human perception, the moon appears as it is now. When you look at the sun, the light you see has taken longer to arrive. The average distance from Earth to the sun is about 150 million kilometers. Light takes roughly 8 minutes and 20 seconds to travel that distance. So the sunlight that warms your skin or brightens the room left the sun several minutes earlier. If, in theory, the sun were suddenly to change, the Earth would not see the change or feel its effects instantly. There would be about an 8-minute delay. In this way, the sun you see in the sky is already slightly a view of the past. As the distances grow larger, the travel time for light becomes more noticeable. Distances within the solar system are often still measured in kilometers or astronomical units, where 1 astronomical unit is the average distance between the Earth and the Sun. However, when astronomers talk about distances to stars and galaxies, the numbers become so large that a more natural unit is based on light's travel time. This is where the light year comes in. A light year is the distance that light travels in 1 year in a vacuum. Because light moves about 300,000 kilometers each second, and there are roughly 31.6 million seconds in a year, a light year is about 9.46 trillion kilometers. This is not a measure of time in this context, but a measure of distance defined by time. When an astronomer says that a star is 10 light years away, they mean that its light takes 10 years to reach us and that the star is about 10 times 9.46 trillion kilometers away. The nearest star system beyond the Sun is a group called Alpha Centauri, which includes Proxima Centauri, a small red dwarf star that is the closest known star to the Sun. Proxima Centauri is about 4.2 light years away. That means the light arriving from it tonight left around 4.2 years ago. If a change occurred on that star today, no one on Earth would see the effect of that change until more than 4 years in the future. Every point of light in the night sky, apart from the planets and the moon, is part of a star whose light has traveled for years, decades, centuries, or more to reach your eyes. Within our own galaxy, distances are often expressed in thousands of light years. The Milky Way, the galaxy that contains our solar system, is a large disc-shaped collection of hundreds of billions of stars, mixed with gas and dust, and dark matter whose presence is inferred by its gravitational effects. The Sun is located in one of the galaxy's spiral arms, roughly 2/3 of the way out from the center. The diameter of the Milky Way's visible disk is on the order of 100,000 light years. This means that light crossing from one side of the galaxy to the other would take about 100,000 years to complete its journey. When you look toward the center of the Milky Way on a dark, clear night, you see a dense band of stars and glowing clouds of gas. The light from these regions can have travel times of thousands to tens of thousands of years. In this sense, the Milky Way is not just a spatial structure, but also a layered record of times. Stars closer to you are seen as they were in the relatively recent past, while more distant stars and clusters are seen as they were tens of thousands of years ago. Beyond the Milky Way, other galaxies lie at even greater distances. The Andromeda Galaxy, the nearest large spiral galaxy similar in size to our own, is about 2.5 million light-years away. This means the light that reaches you from Andromeda tonight began its journey long before human civilization arose, traveling across intergalactic space for millions of years. When you see its faint smudged glow through a telescope or in long exposure images, you are looking at a very old snapshot of a distant galaxy's past. At even larger distances, light travel times extend to hundreds of millions or even billions of years. Some of the farthest galaxies visible with powerful telescopes are seen as they were only a few 100 million years after the universe began. Their light has been stretched and reddened by the expansion of space along its path, and by the time it arrives, the galaxies themselves may have changed drastically or merged with others. In this way, the sky holds a kind of natural archive, where looking farther out is the same as looking farther back in time. The speed of light also plays a central role in the theory of relativity. According to this theory, the speed of light in a vacuum is the same for all observers, no matter how they are moving. This leads to surprising consequences. Measurements of time and distance depend on the relative motion of observers. As objects move closer to the speed of light, time for them as measured by an outside observer appears to slow down. Lengths in the direction of motion appear contracted. These effects are not noticeable at everyday speeds, but become important for particles in accelerators or for spacecraft hypothetically traveling at significant fractions of light speed. In practical terms, the finite speed of light introduces small but important delays in communication over large distances. Signals sent from Earth to spacecraft near other planets take time to arrive. For example, when Mars is relatively close to Earth, the one-way light travel time can be around 3 to 20 minutes, depending on the positions of the two planets in their orbits. When engineers send commands to a rover on Mars, they know that the rover will only receive them after this delay, and any signals sent back will also take minutes to return. This makes real-time control impossible over such distances. Instead, sequences of instructions must be sent in advance. On an even shorter scale, the speed of light underlies technologies like global positioning systems. Signals from satellites orbiting Earth travel at the speed of light and are used to calculate positions on the ground. To determine a receiver's location accurately, the system relies on precise timing. The small differences in the arrival times of signals from several satellites allow the receiver to triangulate its position. Because the speed of light is finite, each nanosecond of timing error corresponds to roughly 30 centimeters of distance error. This is why extremely accurate clocks are so important for navigation systems. Thinking about these distances and travel times in a calm nighttime setting can be quietly soothing. It is not necessary to hold every number in mind. Instead, you can simply allow the general idea to rest with you. Light moves very fast, but not infinitely fast, and over the immense spaces between stars and galaxies, even that great speed translates into long journeys. The starlight that gently falls through your window or glows in the sky has been on its way for years or longer, crossing spaces so empty and quiet that nothing interrupted its path until it reached the earth. In a sense, the night sky is a mosaic of different pasts. Closer stars show you relatively recent moments, while more distant stars and galaxies show older epochs of the universe. Yet from your perspective, all of this light arrives together in the present, forming a single unified scene above you. Time and space intertwine. Distance is encoded in the delay, and the farther you look, the earlier the universe you see. This connection between distance, time, and light also means that the universe beyond a certain limit cannot be observed directly. Because the universe has a finite age and light takes time to travel, there is a maximum distance from which light has had time to reach us. Beyond that horizon, regions may exist but remain unobservable, not because they are hidden behind objects, but because there has not yet been enough time for their light to arrive. For the purpose of relaxing and drifting towards sleep, it can be enough to know that the observable universe has a kind of temporal boundary as well as a spatial one, defined by the time light has had to travel since the universe began expanding. As you rest, you are part of this vast network of distances and times. The room is small on cosmic scales, yet it sits within a solar system that orbits a star, which orbits the center of a galaxy, which itself is one of many galaxies in the observable universe. Light from remote places is continuously arriving, carrying quiet messages from events that happened long ago. Meanwhile, the light from your own star, the sun, has taken only minutes to reach you, guiding the rhythms of day and night that structure your life. In the next section, the focus will turn more directly to the idea of space-time and the gentle curves associated with gravity. Building on the finite speed of light and the interlocking nature of time and distance, the narrative will explore how gravity is understood not just as a force, but as a subtle warping of the very fabric that combines space and time, always keeping the tone soft and slow, suitable for drifting deeper into rest. To understand how time and space connect even more deeply, it helps to return to the idea of space-time. In everyday experience, space and time feel separate. You can point to where something is and you can say when it happened. In modern physics, however, they are combined into a single four-dimensional framework, with 3 dimensions describing position and 1 describing time. This framework allows events to be located using both their place and their moment, forming a unified description of the universe's unfolding. Within this view, gravity is not only a force pulling objects together, but also a reflection of how mass and energy shape space-time itself. Massive objects such as planets, stars, and galaxies cause space-time to curve around them. Other objects and even light then follow paths that are straight in the curved space-time, which when seen from a distance appear as arcs and orbits. This concept, originating in the general theory of relativity, replaces the idea of gravity as an invisible force acting across empty space with the idea of motion guided by geometry. Although the mathematics behind this is complex, the core idea can be held gently. Imagine space-time as a smooth, continuous medium that can be bent or stretched by the presence of mass and energy. Where there is more mass, space-time is more curved. A planet orbiting a star is not being pulled by a force in the traditional sense. Instead, it is following the straightest path available in the curved space-time around the star. From your perspective, that path appears as a closed orbit, repeating over and over as time passes. This curvature does not only affect the paths of objects in space, it also influences the flow of time itself, In regions of stronger gravity closer to massive objects, time passes more slowly compared with regions farther away. This effect is known as gravitational time dilation. If two identical clocks are placed at different distances from a massive body, the clock closer to the mass, where gravity is stronger, will tick more slowly relative to the one farther away. The difference is usually very small but can be measured with extremely precise clocks. On Earth, this means that time at the surface passes slightly more slowly than time at higher altitudes. A clock on a mountaintop will tick a tiny bit faster than an identical clock at sea level. The difference is not something you can sense directly. It is far too small to affect daily life in any noticeable way. Yet it exists, and careful experiments with atomic clocks have confirmed it. This subtle variation in the rate of time is one of the ways in which the unity of space and time becomes visible in physical measurements. These effects are important for technologies that depend on highly accurate timing, such as satellite-based navigation systems. Satellites orbit at altitudes where gravity is slightly weaker than at the Earth's surface, and they also move at high speeds relative to the ground. Both factors, gravitational time dilation and the time dilation associated with motion, affect the rate at which their onboard clocks run. Without correcting for these relativistic effects, the timing signals from the satellites would gradually drift, and position calculations would become inaccurate. By including these corrections, the system maintains the precision needed for navigation. At much stronger gravitational fields, near extremely dense objects like neutron stars or black holes, the curvature of space-time becomes more pronounced. In such environments, the difference in the flow of time between different locations can be extreme. From a distant observer's point of view, an object falling toward a black hole appears to slow down, its signals stretching out and fading as it approaches a region from which light cannot escape. For the falling object itself, time continues to pass normally according to its own clock. But the external view highlights how differently space-time can behave under intense gravity. Closer to home, in the gentle gravity of Earth, these relativistic phenomena are present but subdued. Yet they still mean that there is no single absolute time that applies everywhere. Instead, time is always connected to an observer and their position and motion within space-time. The idea of a universal, perfectly synchronized clock throughout the universe is replaced by a more nuanced picture, where each path through space-time carries its own measure of duration. Despite this complexity, the overall behavior of gravity on human scales remains reassuringly predictable. Objects fall toward the ground, planets follow orbits, and the tides rise and fall in patterns that can be calculated and anticipated. The geometric interpretation of gravity does not change these familiar experiences. It simply offers a deeper explanation of why they occur, linking them to the shape of space-time rather than to forces acting across empty distances. Gravitational effects also influence light. Light normally travels in straight lines, but in curved space-time, those straight lines bend as they pass near massive objects. This bending of light, known as gravitational lensing, has been observed in many astronomical contexts. Light from distant galaxies can be deflected by the gravity of closer galaxies or clusters, creating arcs, multiple images, or subtle distortions in the observed shapes. These patterns provide evidence for the distribution of mass, including matter that cannot be seen directly, such as dark matter inferred from its gravitational influence. The existence of gravitational waves adds another layer to the picture. These are ripples in space-time itself, generated by accelerating masses, particularly by violent events like pairs of massive objects spiraling together and merging. As these waves pass through a region, they cause extremely small temporary changes in distances, stretching and compressing space-time in alternating directions. Sensitive detectors on Earth have measured these waves, confirming predictions of general relativity and offering a new way to observe cosmic events. For a listener preparing to sleep, the intricate details of equations and measurements are not necessary. What matters is the gentle understanding that gravity is not only a familiar downward pull, but also a reflection of how the universe's underlying structure is shaped by mass and energy. The same principle that guides a falling apple or a resting body on a bed also governs the motions of planets and the flow of time near massive objects. This unified view of gravity and space-time connects the very local experience of weight and rest to the large-scale architecture of the cosmos. As you feel the bed supporting you, you are experiencing the Earth's gravity, which is one manifestation of the curvature of space-time created by the planet's mass. The fact that you do not drift away but remain gently held against the surface is part of the same physical story that explains why the moon orbits the Earth and why the Earth orbits the sun. In a quiet room at night, these ideas can serve as soft background thoughts. The body rests in one small region of curved space-time, while on larger scales, stars and galaxies follow paths determined by the same underlying geometry. Time flows a little differently at different heights and in different gravitational fields, but these differences are so small in ordinary settings that life unfolds with a sense of steady continuity. The complexity of space-time remains mostly hidden, revealed only in precise measurements or extreme astronomical phenomena, while day-to-day experience is simple and stable. As the script continues, the next section will shift to the expanding universe and the faint, pervasive glow left from its early stages. Together, these ideas, space-time curvature, gravitational effects on time, and the large-scale evolution of the cosmos, combine into a softly framed picture of a universe that is dynamic yet orderly, vast yet described by consistent principles, all continuing quietly as you drift further towards sleep. On the largest scales, space itself is not static. Observations of distant galaxies reveal that overall they are moving away from one another, as if the universe is gently stretching over time. This behavior is described by the idea of cosmic expansion. Rather than galaxies flying outward through a pre-existing space, the distances between them grow because the underlying fabric of space is expanding. Nearby galaxies, like those gravitationally bound to the Milky Way, can move toward us, but when looking far enough out, the general trend is one of increasing separation. This expansion was first recognized by studying the light from distant galaxies and noticing that it is shifted toward longer, redder wavelengths. The more distant a galaxy is, the stronger this redshift tends to be. Interpreted within the framework of general relativity, this pattern suggests that the space between galaxies has been stretching while the light traveled, lengthening its wavelength. The relationship between distance and redshift provides information about the rate at which the universe is expanding and how that rate has changed over time. When this expansion is traced backward using both observations and theory, it suggests that the universe was once much denser and hotter. In that early state, matter and radiation were closely coupled, and the universe was filled with a bright, opaque glow. As it expanded, it cooled, and at a certain point it became transparent, allowing light to travel freely through space. The remnant of this early light is still present today, not as visible light, but as a faint, nearly uniform microwave radiation that fills the sky in every direction. This radiation is known as the cosmic microwave background. It can be measured with specialized instruments and appears as a very even glow at a temperature of just a few degrees above absolute zero. Tiny variations in its temperature across the sky, only a small fraction of 1%, carry information about the slight irregularities in the early universe, regions where matter was slightly more or less dense. Over billions of years, gravity amplified these small differences, leading to the formation of galaxies, clusters, and other large structures. The cosmic microwave background provides a kind of image of the universe as it was shortly after it became transparent, when it was only a small fraction of its current age. By comparing detailed measurements of this background with theoretical models, scientists can estimate key properties of the cosmos, such as its overall age, its average composition, and how its expansion has evolved. These comparisons support the view that the universe is about 13.8 billion years old, and that it has been expanding for most of that time. On large scales, the composition of the universe appears to be dominated by forms of matter and energy that are not directly visible. Ordinary matter, the kind that makes up stars, planets, gas, dust, and living organisms, accounts for only a relatively small fraction. A much larger portion seems to be made of dark matter, a type of matter that does not emit or absorb light but exerts gravitational influence. Evidence for dark matter comes from the way galaxies rotate, from the behavior of clusters of galaxies, and from gravitational lensing patterns that cannot be explained by visible matter alone. In addition, observations indicate that the expansion of the universe is not just continuing but accelerating. This acceleration suggests the presence of a form of energy associated with space itself, often called dark energy. Dark energy appears to act as a kind of uniform pressure that drives galaxies apart more rapidly over time. Its exact nature remains uncertain, and it is one of the major open questions in cosmology. In describing dark matter and dark energy, scientists move partly into the realm of inference and speculation. Guided by data but not yet equipped with a complete, detailed understanding of what these components are at a fundamental level. Despite these uncertainties, the broad outline is clear. The universe began in a hot, dense state, expanded and cooled, formed atoms, stars, and galaxies, and now continues to expand, with its rate of expansion influenced by both matter and dark energy. On human timescales, these changes are incredibly slow. The distances between widely separated galaxies increase over millions and billions of years, while the view of the sky during a single lifetime remains largely the same, with only subtle shifts detectable through careful observation. Thinking of the expanding universe in a calm nighttime setting can bring a sense of spaciousness. While you rest in one small place, the larger cosmos is gently evolving, but it does so gradually, following patterns that extend far beyond any individual day or year. The stars you see at night belong to a galaxy that itself is moving through space, participating in the large-scale motion of cosmic structures, all while the background glow from the early universe remains faint and steady in every direction. From your perspective, lying still, these enormous processes are silent and remote. The expansion of space does not stretch objects held together by stronger forces. Atoms, planets, and galaxies remain bound. The room does not expand, your body does not drift apart, and local physical laws remain stable. The expansion becomes significant only on scales much larger than galaxies, where gravity is too weak to overcome the general tendency of space to stretch. This allows life and matter to remain cohesive even as the universe as a whole grows. In this picture, time acquires an additional dimension of meaning. Not only does time measure the sequence of events in your own life and in Earth's history, it also measures the unfolding of the universe from its hot, dense beginnings to its present state. The cosmic microwave background marks a milestone in that history, a time when the universe transitioned from opaque to transparent. Each galaxy you see is another chapter, representing different stages of star formation and evolution. As the universe continues to expand, its long-term future is still the subject of research and discussion. Current models based on observed acceleration suggest that expansion will keep going and may even become more pronounced. Over extremely long spans, galaxies not gravitationally bound to one another will appear to recede faster and faster, in the sense that their light will be more and more red-shifted. Eventually, distant galaxies may fade from view as their light stretches beyond detectable wavelengths. These projections are based on current observations and theories, and while they are grounded in data, they still involve extrapolations far into the future, which carries some degree of uncertainty. For the sake of rest and sleep, it is not necessary to dwell on these distant futures in detail. Instead, it can be enough to hold a gentle awareness that the universe is dynamic and that you are living at a particular moment in its long history. The cosmic microwave background is a relic of its youth. The stars overhead are part of its middle chapters. Your own life, measured in decades, occupies a brief interval in this ongoing story, and tonight's sleep is a small, recurring pause within it. As you breathe slowly, you might imagine the universe as a vast, quiet expanse in which galaxies drift apart over immense times. The faint background glow, invisible to your eyes but measurable with instruments, fills all of space with a soft, uniform signal from the past. Against this backdrop, your own room is a small, stable island of familiarity, unaffected by expansion except in the abstract, allowing you to rest securely while the cosmos continues its gentle evolution. In the next section, the focus will return more directly to the interaction between cosmic time and personal time. How sleep, memory, and nightly rhythms fit into this wide context. The aim will be to connect the large-scale processes just described with the intimate experience of drifting to sleep, showing how both exist together within the same universe, governed by the same physical principles, unfolding at their own appropriate scales. As the universe expands gently across billions of light years, your own body goes through another kind of quiet transformation. Each night, as the circadian system signals that it is time for rest, the brain shifts from wakefulness into sleep, passing through a series of stages that allow for repair, consolidation of memory, and restoration of mental and physical resources. This nightly cycle is one of the most regular and essential rhythms in human life, closely tied to the turning of the earth and the patterns of light and darkness that have shaped all life on this planet. Sleep is not a single uniform state, but a progression through different levels of activity in the brain and body. When you first lie down and close your eyes, the transition begins. The brain gradually reduces its alertness signals, muscle tension eases, and heart rate and breathing slow. This early phase is light sleep, a boundary state between wakefulness and deeper rest. It is easy to be awakened from this stage, and awareness of sounds or sensations may still drift in and out. As sleep deepens, the brain shifts into what is known as slow-wave sleep, characterized by large, synchronized electrical rhythms that sweep across the cortex. This stage is associated with the deepest rest and the most restorative effects on the body. Growth hormone levels may rise, tissues repair themselves more actively, and the immune system becomes more engaged. During this phase, responsiveness to the outside world is reduced, and the sense of time often fades entirely. Minutes can pass without any internal registration, leaving the sleeper unaware of their duration until waking. After a period of deep sleep, the brain typically shifts into a different mode called rapid eye movement sleep or REM sleep. During this stage, the electrical activity of the brain becomes more similar to wakefulness, but the body is largely paralyzed, preventing movement. This is when most vivid dreaming occurs. Dreams can feel long or short, coherent or fragmented, depending on the structure of the narrative and the emotions involved. The relationship between dream time and real time is complex, as discussed earlier. But on average, they seem to align roughly, even though subjective perception within a dream can vary widely. Over a typical night, the brain cycles through these stages multiple times, with each cycle lasting roughly 90 minutes. Early in the night, deep slow-wave sleep is more prominent. As the night progresses, REM periods become longer and more frequent, and slow-wave sleep becomes less pronounced. This pattern is not random, but reflects the interaction of sleep-regulating systems in the brain, designed to balance different kinds of recovery and mental processing. One of the key functions of sleep is the consolidation of memory. During wakefulness, the brain is constantly taking in new information, sights, sounds, facts, skills, and experiences. Much of this information is initially held in a temporary, fragile form. During sleep, especially during slow-wave and REM sleep, the brain appears to replay and reorganize these memories, strengthening some connections while pruning others. The result is that memories become more stable and integrated, better able to be recalled and used in the future. Sleep also supports emotional regulation. When sleep is sufficient and of good quality, emotional responses tend to be more balanced, and the ability to cope with stress is enhanced. When sleep is restricted or disrupted, emotional reactivity can increase and negative emotions may be harder to regulate. This link between sleep and emotion reflects the way sleep influences the connectivity and activity of brain regions involved in mood and decision-making. As you lie in the dark and listen, the conditions for sleep are already in place. The circadian clock described earlier has signaled the biological night. Melatonin levels are rising, body temperature is declining, and the brain's arousal systems are winding down. External cues such as darkness and quiet support this internal shift, helping to remove distractions that might keep the mind alert. The combination of these signals creates a gentle push towards sleep, a state that the body is prepared to enter without conscious effort. The sense of time during this transition is particularly fluid. As attention drifts, the usual markers that help the mind track minutes and hours become less clear. Thoughts may wander in loops or fragments, without the sharp focus that characterizes wakefulness. External sounds may seem to come from a distance, and the boundary between internal and external sensations can blur. This loosening of temporal structure is part of the natural process of falling asleep, as the brain releases its hold on vigilance and detailed awareness. In this state, thinking about large cosmic timescales can paradoxically be calming. The universe has been expanding for billions of years. Stars have formed and faded across immense intervals, and light has traveled across space for epochs longer than human history. Against this vast backdrop, the few hours of your own sleep occupy an infinitesimally small moment. Yet those hours are meaningful and necessary for your own well-being. They provide a time when the body and mind can turn inward, disconnected from immediate demands and focus on repair and renewal. There's also a kind of symmetry between cosmic rest and personal rest. The universe in its expansion follows predictable physical laws without needing any conscious guidance. Stars burn their fuel according to the equations of nuclear physics. Planets orbit according to the geometry of space-time, and light travels at a constant speed, all without any intervention. Similarly, your own body has systems that guide sleep without requiring conscious control. The circadian clock ticks, sleep stages cycle, and memories consolidate, all managed by neural circuits that function automatically as long as the conditions are right. This means that, as you lie here, you can release the need to manage or force sleep. The biological systems that support it are already at work. The universe continues its slow processes, and you are free to let your own processes unfold. Time, both cosmic and personal, moves forward on its own, carrying you gently from wakefulness into rest. Nighttime is also a period when the usual pace of life slows. During the day, schedules and activities divide time into discrete blocks: meetings, tasks, meals, conversations. At night, especially in the quiet hours, these divisions soften. There may be no appointments to keep and no immediate decisions to make. Time becomes less segmented and more continuous, a gentle flow that does not demand attention or action. In this flow, the mind is free to wander or settle depending on what feels natural. For many people, this shift in the perception of time is one of the most pleasant aspects of nighttime. The pressure to be productive or responsive fades, and the hours become a kind of refuge. Even if thoughts or worries arise, they can often be held more lightly at night, acknowledged without the urgency they might carry during the day. This softness in the quality of time can itself be sleep-inducing, as the mind recognizes that nothing urgent is required and allows itself to drift. Sleep also interacts with the long timescales of life and aging. Over the course of years and decades, consistent sleep patterns contribute to health, cognitive function, and emotional stability. Sleep needs and patterns may change with age, but the fundamental importance of rest remains. Infants and children sleep more, spending larger portions of their days in rest, while adults generally settle into a pattern of nightly sleep that lasts several hours. In old age, sleep may become lighter or more fragmented, but it still serves essential functions, supporting the body's ongoing maintenance and the mind's processing of experience. From a broader perspective, sleep is part of the way living organisms adapt to the rhythms of a rotating planet. The alternation of day and night has been a constant feature of Earth's environment for billions of years, and sleep is one evolutionary response to that pattern. It allows organisms to time their activity to match favorable conditions, conserve energy during periods when resources are unavailable, and protect themselves during times of greater vulnerability. For humans, sleep remains tied to this ancient cycle, even though modern life allows activity at almost any hour. As the script moves toward its conclusion, the final section will gently gather these ideas together. The inner clocks and subjective time, the planetary cycles and cosmic expansion, the finite speed of light and the curvature of space-time, and the nightly experience of sleep. The aim will be to leave you with a soft, integrated picture of time and space, one that supports the quiet sense that, as you rest, you are part of a coherent, orderly universe, unfolding at many scales, all of them connected by the same underlying principles. As the night deepens and your body becomes heavier against the surface supporting you, All the pieces of time and space described so far can settle into a single quiet picture. Close at hand are your own inner clocks, the circadian rhythms guiding hormone levels, body temperature, and sleepiness, moving through their nightly pattern whether you pay attention to them or not. Within your brain, networks that track seconds and minutes have begun to loosen their grip, making time feel softer and less sharply divided, while memory systems prepare to sift through the day's experiences and fold them gently into longer-term storage during sleep. Around you, the room is still, yet on the scale of the planet, motion continues. The Earth slowly turns on its axis, carrying your location through the night toward the next sunrise. One rotation defines the day that structures your waking and sleeping life, while the orbit of the Earth around the Sun sets the length of the year, guiding the changing seasons of light and darkness. The tilt of the planet's axis decides whether your nights are short and warm or long and cool. But from moment to moment, the turning is smooth and unhurried, offering a reliable backdrop for rest. Beyond the atmosphere, in the thin darkness of near-Earth space, satellites circle the planet, their paths and timing influenced by gravity and, in subtle ways, by the relativistic effects of speed and altitude. Each satellite carries precise clocks that help determine positions on the Earth's surface, quietly relying on the same principles that say time flows a little differently at different heights in a gravitational field. Even here, the abstract ideas of space-time and time dilation touch everyday life, though these refinements remain invisible as you lie in bed, simply trusting that the world outside continues as usual. Farther out, the solar system orbits within the Milky Way, our home galaxy. The sun shines steadily, fusing hydrogen into helium in its core, releasing light that crosses the space to Earth in just over 8 minutes. Around it, planets follow their orbits, guided by the curved geometry associated with the sun's mass. Asteroids and comets trace more elongated paths, some visiting the inner regions only occasionally. All of these bodies move in accordance with gravity's quiet rules, forming a stable environment in which Earth's own cycles of day, night, and season can proceed with remarkable regularity. The Milky Way itself is a broad, rotating disk of stars, gas, dust, and dark matter, tens of thousands of light-years across. The Sun and its planets are not at the center but partway out, orbiting the galactic center over hundreds of millions of years. While you experience a human lifetime as a span of decades, the Sun's journey around the galaxy is so slow that, during your entire life, it completes only a tiny fraction of its orbit. The patterns of stars you see at night change only slowly over many generations, and yet, in the long story of the galaxy, they too evolve and rearrange. Beyond the Milky Way, countless other galaxies occupy the observable universe. Some are small and irregular, others large and structured with clear spiral or elliptical forms. Light from many of these galaxies has traveled for millions or billions of years before arriving here, carrying images of how they looked when the universe was younger. The large-scale expansion of space means that, on average, distant galaxies drift away from one another, their light stretched to longer wavelengths during its long journey. This expansion is gentle on human timescales, affecting vast cosmic distances but leaving local structures, atoms, planets, stars, and galaxies bound together. All of this unfolds within space-time, the unified arena where positions and moments are linked. Mass and energy tell space-time how to curve, and that curvature tells matter and light how to move. This relationship underlies the orbit of the Earth, the fall of an apple, the bending of light around massive objects, and the slow differences in the rate of clocks at different heights. In your daily life, these effects blend into a seamless experience of gravity as weight and of time as a steady flow. Even though, on closer inspection, time is slightly different at each position, and space can be gently curved by mass. Set against this immense orderly structure, your own nightly sleep is both very small in scale and deeply integrated into the same physical reality. The atoms in your body were forged in ancient stars that lived and died long before the sun formed. The processes that allow neurons to fire, muscles to relax, and hormones to rise and fall are governed by the same physical constants that define the speed of light and the strength of gravity. The rhythms of your sleep are shaped by the rotation of the earth and the pattern of light and darkness that falls across its surface each day. As you drift towards sleep, the sense of self moving through time can soften. The divisions between seconds and minutes between today and tomorrow become less important. Instead, there is the simple awareness of breathing, the feeling of contact with the bed, the quiet in the room. Thoughts about large cosmic timescales, billions of years, the age of the universe, the slow expansion of space, can be allowed to fade into the background. They remain true, but they no longer need active attention. They are part of the environment in a broad sense, like a distant, slow-moving weather pattern, while your focus settles on the immediate calm of rest. It can be reassuring to know that while you sleep, almost everything that matters in the physical world will continue in a smooth, predictable way. The earth will keep turning. The moon will continue its orbit, the sun will shine, and the galaxy will move through space. The cosmic microwave background will continue to fill the universe with its faint, uniform glow. On more immediate scales, your internal clocks will keep time, guiding the stages of sleep throughout the night, and your brain will quietly process memories and emotions, sorting and integrating them without disturbing your rest. In this sense, falling asleep is a form of trust in the stability of time and space. You allow consciousness to recede for a while, confident that the physical structures that support you, from your own body to the planet beneath you, will remain reliable. The basic laws governing motion, energy, and gravity do not change from night to day. The circadian rhythms will continue their cycle, preparing you to wake again when the next morning's light returns. The continuity of these processes makes it possible to let go, knowing that the universe does not require your constant vigilance to carry on. As your breathing remains slow and steady, you might picture yourself as resting in a small, calm corner of a very large, orderly system. The universe is ancient, vast, and still unfolding, but it is also governed by consistent principles that apply everywhere, from the farthest galaxies to the cells in your body. Time and space, so immense in scope, also accommodate the quiet span of your night's sleep, giving that small interval a secure place in the whole. If your eyes are still open, they may feel heavier now, more inclined to close with each passing sentence. If they are already closed, the words can simply be a soft backdrop, something for the mind to rest against as it lets go of the need to stay alert. There is nothing to solve and nothing to remember. The science of time and space, from inner clocks to cosmic expansion, has done its work for tonight. Not to demand effort, but to provide a calm, coherent story within which you can safely drift. As this journey through sleepy science facts about time and space comes to an end, there is only a gentle, unobtrusive invitation. If you found this quiet exploration soothing, if it helped you feel a little more at ease while learning something along the way, you are warmly welcome to let this channel keep you company on other nights as well. When it feels right, you can softly tap to like the video or subscribe, so that more calm stories and sleepy science explorations can reach you whenever you need them. Quietly, slowly, and always with the same peaceful tone that invites you to rest.